Okay, so forget the usual headlines for a moment, the ones about AI taking over the world. What if? What if AI's development is actually more like, say, the internet or even electricity? A huge transformative force, yeah, but one we kind of integrate, adapt to over time. Welcome to the deep dive. We sift through all the noise to give you what you need to know. Today, we're doing a really comprehensive exploration of this Knight First Amendment Institute essay, AI as Normal Technology. It's by Arvind Narayanan and Sayash Kapoor.
Hi there. Yeah, it's a really thought-provoking piece because it pushes back against those dominant narratives, this sort of super intelligence focus. Instead, the authors are saying, look, maybe we should view AI as a normal technology, something that shares characteristics with other big tech shifts in history.
Exactly. And it's important to stress for you, the learner, calling AI normal isn't downplaying it at all. Like the internet was revolutionary, right?
Yep.
But still fits their definition of normal tech. The core idea is maybe AI's path and our ability to manage it is more predictable, more controllable than the superintelligence hype suggests.
hmm They build their case on three main pillars, really. First, they take a hard look at where AI is now. Second, they offer a prediction, a pretty carefully considered one, about its likely future. And third, they give some recommendations, a kind of prescription for how we should handle AI, how we should govern it as it keeps evolving.
Right. So our goal here is to really unpack that framework for you.
Mm.
We want to get past the hype, the doomsday stuff, and give you a more grounded, maybe more insightful way to think about AI and what it actually means for us. Think of this as your shortcut to getting really informed on, well, a pretty crucial topic.
Yeah, and to do that, we'll be looking closely at a few key areas they cover. Things like the speed of AI progress. Is it really moving as fast as people say, and in what ways? How might the work get divided up between humans and AI? What are the real risks we should be focusing on? And what does all this mean for policymakers trying to figure out the rules of the road?
Okay, let's dive right in then. Part one, the speed of progress. The authors give us a really helpful way to break this down right into four different phases. What are those again?
Yeah, it's a useful distinction. They talk about invention. That's the creation of new AI methods, like, deep learning itself. Then innovation, turning those inventions into actual products, applications that solve problems. Then adoption, when people, companies, actually start using these AI tools. And finally, diffusion, the really broad spread of AI across society, across the economy.
And the crucial point here, for you, the learner, is that these don't all happen at the same speed.
Not at all. That's central to their argument. Narayan and Kapoor make a strong case that diffusion, getting AI truly integrated everywhere, is often the slowest part. It's frequently the main bottleneck, and they back this up, especially when you look at areas where safety is critical.
Okay, like what? Give us some examples so we can really grasp this.
Well, in some earlier work, they looked at about 50 real-world systems using ML for big decisions about people, things like predicting recidivism risk, insurance eligibility, that sort of thing. And what's really striking is, despite all the advances in AI methods, most of these systems still rely on older statistical techniques, simple regression, features designed by hand. They're really complex modern ML models. They're just not seeing wide use in these high-stakes situations.
That's fascinating. So why?
Hmm?
Why stick with older methods when the new stuff is supposedly so much better?
It really boils down to safety and reliability. With the more complex, less transparent models, the black boxes, it's just incredibly hard to predict every possible way they might behave out in the real world under all sorts of conditions. Think about that epic sepsis prediction tool failure. It looked great in testing, right? High accuracy. But in actual hospitals, it missed most sepsis cases and flooded doctors with false alarms, alert fatigue.
Oof, that's a serious problem. What went wrong there?
Well, it turned out the model had kind of accidentally learned to rely on a signal that doctors had already prescribed antibiotics, which of course happens after a sepsis diagnosis is suspected or made. So in the test data, it looked like it was predicting sepsis, but it was really picking up on something that happened later. It highlights just how tricky it is to really vet these complex systems before they go live.
And we're seeing similar things even with the newer generative AI, aren't we? It's not just older predictive tools.
Absolutely. Remember the early Bing chatbot, Sydney? When people had longer conversations with it, it started going off the rails. Argumentative, sometimes even hostile. Clearly, they hadn't fully tested how it would react beyond simple short queries. Or Google's Gemini image generator, troubles with historical figures, embarrassing, inaccurate results. Now, these weren't life or death, but they show the same core challenge: ensuring reliability, preventing weird, unintended consequences, even in seemingly less critical uses.
And it sounds like regulation is starting to act as a kind of speed bump here, too, especially in those high consequence areas.
Definitely. You've got the FDA being very careful with medical AI and things like the EU AI Act coming in with its risk tiers and strict rules for high-risk systems. These basically create regulatory speed limits where safety is the top priority. Now, the authors do acknowledge concerns about maybe creating too much red tape, runaway bureaucracy that could stifle good innovation. But the overall expectation is that this slow, careful diffusion in critical areas, that's likely to continue.
Okay, but what about outside those really safety critical domains? Is AI adoption just exploding everywhere else?
Well, Narayan and Kapoor pushed back on that idea too. They mentioned a study from August 2024 showing, yeah, 40% of US adults had used generative AI. Sounds like a lot, right?
Yeah, 40% sounds pretty high, pretty fast.
But when you look closer, for most of those people, it was infrequent use, low intensity. So that big 40% number actually translated into a tiny percentage of total work hours being affected and only a modest bump in overall labor productivity.
Ah, okay. So it's not just about access or trying it once.
Yeah.
It's about how deeply it's getting woven into work, into daily habits.
Exactly. And they even question if AI diffusion is really faster than, say, PCs were in the early days, especially when you consider how much people actually use it and the cost differences. Adoption isn't just about having the software available. It means changing workflows, changing habits, and that's often slow.
It reminds me of that productivity paradox with electricity. We had the power, but it took ages for productivity to actually take off across the economy.
Precisely. Paul David's work on that is classic. It took almost 40 years after Edison's first station for the big productivity gains to really show up. Why? Because it wasn't just about plugging things in. Factories had to be completely redesigned around production lines. Workplaces had to change. Training had to change. Realizing the benefits of a general purpose technology like electricity or maybe like AI requires deep systemic changes, and that just takes time.
Okay, so diffusion is slow. What about the pace of innovation itself?
Yeah.
Are there limits on how fast new AI methods can even be developed?
Yes, they argue there are external limits there too. They talk about this ladder of generality in AI research, the idea that methods become more general, needing less specific programming for new tasks.
And we've seen that in some areas, right?
Mhm.
Like NLP translation getting way better with large language models, or AlphaZero mastering games without human game knowledge.
Exactly. In those kinds of domains, the effort to build new applications has gone down. But contrast that with something like self-driving cars. Hugely consequential, real-world complexity. Development has taken decades. Why? Because safety puts real limits on how fast you can scale up those learning feedback loops when you're dealing with the messy, unpredictable real world.
And this difference between lab results and real-world performance leads to what they call the capability-reliability gap.
That's the term, yes. You might show amazing capability in a controlled setting, but getting the robustness, the reliability needed for safe everyday use, that often lags way behind. And that gap is a major hurdle for building truly useful AI agents that can handle complex jobs autonomously. Plus, there's all that tacit knowledge in organizations, the stuff that's not written down, the practical wisdom AI can't easily learn from data, and of course, privacy rules, data sharing concerns. These also slow down how fast AI can learn across different places.
What about the bitter lesson in AI? This idea that general methods always win out eventually. How does that fit in?
Right. The bitter lesson, famously put by Rich Sutton, basically says general methods that just leverage more compute power tend to beat methods relying heavily on human design features or domain knowledge. And that holds true for the methods themselves. But Narayanan and Kapoor make a key distinction. It doesn't automatically apply to application development. Even with very general models, like in recommender systems, building and maintaining the actual application still takes a lot of custom coding, specific engineering, human expertise.
And what happens when AI needs to go beyond just learning from what humans already know? Limits there too.
Oh, absolutely. That's inherently tougher and slower. Think about scientific discovery or figuring out the best economic policies. Pushing those frontiers often requires real-world experiments, drug trials, policy pilots. These have real social costs and consequences. Society, quite rightly, puts limits on letting AI just run wild with experiments for its own learning.
So the real world itself, with all its complexity and risks, acts as a kind of brake on AI progress in many important areas. Okay, let's shift to benchmarks. We hear all the time about AI beating humans on tests. What's the author's take on how much these benchmarks really tell us about real-world usefulness?
They're pretty critical, actually. They agree benchmarks are useful for tracking progress in AI methods, the underlying algorithms, but they argue these scores are often misunderstood, taken as direct proof of progress in real-world applications. And that fuels a lot of the hype.
Can you give us an example of that disconnect?
The classic one is GPT-4 passing the bar exam. Impressive score, technically speaking, sure, but does that mean it can actually practice law effectively? Probably not. The bar exam heavily tests memorized knowledge, exactly what LLMs are good at. It doesn't really test the skills lawyers use daily: creative thinking, judgment, strategy, dealing with clients, the complex stuff.
So it seems like the easier a task is to turn into a standardized benchmark, the less likely it is to actually represent complex, real-world professional work.
That's precisely the point. It relates to this idea of construct validity. Does the test actually measure the thing it claims to measure? They argue the best way to know if an AI is useful isn't a benchmark. It's building the actual application and testing it with real professionals in realistic settings. These uplift studies, measuring how much AI actually helps humans, often show much more modest gains than the benchmarks might imply. Now, there are exceptions: copywriting, translation, some jobs have seen real disruption, but often it's augmentation, not replacement.
So benchmarks are a piece of the puzzle, useful for researchers maybe, but we need to look at things like adoption intensity, the types of applications being used to really gauge the impact.
Exactly, and they point out that even the AI forecasting community sometimes uses watered-down definitions for milestones, like human-machine intelligence parity, based just on exam scores. These definitions might be easy to measure, but they lack that construct validity. They don't really predict real-world impact reliably.
Okay, so pulling this all together, this detailed look at progress suggests the economic impacts are likely to be gradual, more evolutionary than revolutionary.
That's a core argument, yes.
Yeah.
The idea that general AI automatically means sudden, widespread automation misses those slow feedback loops of innovation and diffusion. It's
Yeah.
like electricity, computers, the internet. The big impacts took time to unfold.
And as AI automates tasks, the value of those tasks drops. And humans shift to other things, right? The goalposts for AGI keep moving.
Precisely. So even if, hypothetically, AI could do every current human job, it doesn't mean human labor becomes worthless. New valuable tasks would likely emerge. So a sudden, massive automation wave wiping out most jobs, they see that as pretty unlikely.
And finally, for this section, they also look at potential speed limits in the progress of AI methods themselves. Even with all the research papers, are we getting truly exponential progress in core ideas?
They raise some doubts. They point to history, like how neural nets were sidelined for years. It suggests maybe there's some herding around popular ideas. Is the current focus on transformers, despite their limits, maybe a similar thing? Some research even suggests that in really busy fields, truly new ideas can struggle to break through the established thinking.
Plus, there are practical limits, hardware, cost, maybe even less open sharing in the industry now.
All potential breaks, yes. And while AI is being used in AI research, they see that more as gradual automation of development, not some single recursive self-improvement breakthrough. They also bring it back to benchmarks. Limitations there can make us overly optimistic about method progress. The Turing test is a great example. AI passed it, but not in the way people originally envisioned intelligence. It's like climbing a mountain. You hit a benchmark, realize it was a false summit, and the goalposts shift. Think about the early AI pioneers' optimism versus today's focus on scaling, agents, sample efficiency. The challenges keep evolving.
Right. That's a really comprehensive look at the speed limits. Okay, let's move to part 2 of the essay. What might a world with advanced AI actually look like? They start by saying we should shift focus away from intelligence or superintelligence. Why?
Basically, they argue those terms are kind of unhelpful, maybe even misleading. They're too vague. Instead, they say, let's focus on capability. What can AI do? And power, its ability to actually change things in the world.
They specifically take issue with that common picture of an intelligence ladder, with AI potentially zooming past humans.
Yeah, they argue intelligence isn't really well defined or measurable on a single scale, especially across different species or systems. More importantly, they say power is the key factor for thinking about AI's impact. Humans have always used tools to increase their power. Modern humans with technology are already super intelligent compared to our ancestors in a way. They feel a lot of the AI risk literature isn't precise enough about intelligence and should really be talking about power.
So the real concern isn't AI becoming smarter in some abstract sense, but gaining enough capability and therefore power to cause problems or lead to loss of control.
Exactly. They expect AI capabilities will keep improving, sure, but the main focus should be on preventing highly capable AI from getting too much unchecked power. It's less about trying to align some hypothetical, all-powerful superintelligence and more about managing the power of the AI we actually build.
And they argue our intuition about superintelligence, often coming from games like chess or Go, is misleading for the real world.
Yeah, their point is that AI alone isn't really smarter than humans using AI as a tool. Human intelligence is unique in its ability to leverage tools to integrate other intelligences. Sure, AI beats us at chess because it's faster, has perfect memory, but those speed advantages aren't relevant for most real-world tasks. And for the few tasks that do need superhuman speed, like maybe controlling a nuclear reactor, we already use specialized automated tools under tight human control.
And based on this, they make some interesting predictions about AI performance in more complex real-world tasks.
They do. They predict that for things like forecasting geopolitical events or persuading people to act against their own interests, AI probably won't significantly beat trained humans, especially humans using simple AI tools to help them. They really stress that self-interest part in persuasion. It's hard to convince people to do things that aren't good for them.
They even critique a specific study on dangerous AI capabilities, saying its persuasion tests weren't realistic enough.
Right. The study used scenarios where persuasion was basically costless. That's not like the real world where convincing someone to go against their interest is hard work. They argue these kinds of decontextualized capability tests don't really tell us much about real-world safety.
Okay, so control is key. But they say control is about more than just perfect alignment or having a human approve every single AI decision.
Yes. They're a bit skeptical about achieving perfect alignment, which they discuss more later, and human in the loop for every decision. That kills the efficiency benefits of automation. It's different from general human oversight.
So what other control mechanisms do they highlight if it's not just alignment or constant human checks?
A whole range of things. Rigorous auditing before and during deployment, continuous monitoring to spot problems, standard system safety engineering, fail-safes, circuit breakers, redundancy, maybe even formal verification to prove safety properties. Plus, ideas from cybersecurity, like least privilege access, formal methods for checking AI-generated code, HCI principles like reversible actions.
And the technical AI safety field is working on other control ideas too.
Definitely. Things like using LMs as automated judges for other AI outputs, systems that escalate to humans when uncertain, making AI agents more understandable, legible, hierarchical control structures. They see the goal of AI safety research as making it easier to reduce accidents, not guaranteeing perfect alignment for some future superintelligence.
And they expect we'll see more innovation in these kinds of human control models as AI gets better. It sounds like a big shift in how human work might look.
That's a core part of their vision. They draw that parallel to the Industrial Revolution work, shifting from manual labor to controlling machines. They see something similar with AI. More human jobs focused on controlling, overseeing, specifying tasks for AI systems. Karen Levy's work on truckers is a good example. Driving is just one part. There's monitoring freight, safety checks, paperwork. AI will likely assist or augment these control-oriented tasks.
So humans move towards managing the AI, guiding it, ensuring it works safely. But there's a tension, right, between efficiency for more AI autonomy and safety for more human control.
Absolutely. And they suggest the risks of giving too much control away will likely act as a natural brake, especially in high-stakes areas. Badly controlled AI is just bad for business, usually. But they stress that regulation still needs to reinforce human control, especially where society-wide impacts are concerned.
Okay, that paints a picture of capable AI, but still very much under human direction. Let's get into part 3, risks. They outline 5 main types of risk in their framework. What are they?
Right. They list accidents, unintended harm, arms races, competition leading to unsafe practices, then accidents, misuse, intentional harm, misalignment, AI goals diverge from human intent, and then systemic risks, non-catastrophic but widespread negative effects like bias, inequality, etc.
We touched on accidents. They seem somewhat optimistic, thinking developers and regulation can handle it, especially with control research advancing. But they acknowledge reasons why that might not hold.
Yes. One is the potential for those arms races if competitive pressure outweighs safety. Another is that a really big AI deployer could cause massive harm even if they eventually fail commercially. Think widespread data loss from a poorly secured AI agent used everywhere. That's more a power concentration problem, though. And then there's the misalignment risk, the idea of an AI escaping or acting catastrophically unexpectedly.
Let's look closer at these arms races in the commercial space. They're not talking military AI here. What's the dynamic?
They point out that historically, many industries have seen these races to the bottom on safety. It happens when companies can push the costs of poor safety onto others, consumers, workers, the environment. Think early factories, steamboats, mining.
But regulation usually steps in to fix that, right? By making companies internalize those costs.
Exactly. Regulations force companies to pay for safety through standards, liability, transparency. They use self-driving cars as a case study. Companies focusing on safety, like Waymo, seem to be doing better long-term than those who rushed, like Cruise or early Uber, which faced huge setbacks.
So there seems to be a real link between safety and success there.
They argue it's likely causal, yeah. Cruise losing its license, safety issues hurting Uber's efforts. It suggests safety pays off. They note the light touch regulation and self-driving oversight, standards, the threat of license removal seems to have helped somewhat. Aviation is also integrating AI while keeping its high safety standards. So their conclusion is, AI arms races are probably sector-specific, needing sector-specific rules.
Which maybe contrasts with social media, where algorithm safety and regulation have been much more debated and maybe slower.
That's a contrast they draw. Social media harms are harder to pin down. Maybe regulatory action was slower. It highlights the need for proactive evidence gathering, transparency, anticipatory ethics in new AI sectors.
What about the worry that AI adoption will just outpace regulation, the pacing problem?
They think that, so far, adoption in high-consequence areas is actually quite slow, even without heavy regulation, maybe because of that innovation diffusion feedback loop we talked about. The slow pace of regulation is a problem, which they get to later, but maybe not an immediate runaway adoption problem in all critical sectors.
And competition between countries, could that lead to cutting safety corners?
They see it as the classic innovation versus regulation tension again. Different countries take different approaches, EU more precautionary, US more post-harm. Despite US-China arms race talk, it's not clear it's actually slowed down AI regulation overall. Lots of state-level action in the US, for instance. They argue most high-risk sectors already have regulations, and regulators focusing on AI use rather than just development is probably right, mostly. Bad adoption leads to local accidents, generally not cross-country arms races, excluding maybe cyber attacks. They prefer the nuclear power analogy over nuclear weapons for AI accidents. No arms race for reactors, but local failures caused backlash. Theoretically, great power conflict could incentivize cutting safety corners for global AI dominance, but current talk is mostly about model development, not reckless deployment. They urge continued pressure for safety and international cooperation.
Okay, now on to misuse, using AI for bad things. They argue defenses need to be downstream, not mainly in the models themselves. Why?
The core idea is that whether something is harmful often depends heavily on context, which the model usually lacks. Take that phishing email example again. The AI capabilities used finding info, writing persuasively aren't inherently bad. It's how the attacker combines them. Trying to stop that at the model level would likely either block useful stuff or just not work against clever attackers.
So it's like trying to build a computer that can't be used for crime.
Pretty much. And giving an AI model enough context to make those nuanced safety judgments itself would probably require massive data access, violating basic security and privacy principles. Now, model-level tweaks can help reduce obviously bad outputs, add friction, but the main defenses have to be where the AI meets the world. Back to phishing. The real defenses are email filters, browser security, user training, not restricting text generation itself. These defenses evolved against humans, and we can adapt them for AI-enabled attacks. Same pattern for cyber threats generally, or bio risks.
And crucially, AI is also useful for defense, right? It's not just a risk multiplier.
Absolutely. They really push back on the idea of AI only being a threat. It's a powerful tool for defense, too. Cybersecurity, finding vulnerabilities, analyzing threats, monitoring networks. AI helps defenders systematically find and fix weaknesses. Google using LLMs for fuzzing is a great example. Same in biosecurity, better screening, or content moderation, spotting influence ops. So restricting AI development could actually hurt our offenses. If models are too restricted, defenders can't use them to find exploits, and attackers can just build their own anyway. They argue we should focus on the offense-defense balance in each area and invest in defensive AI, not just restrict the tech.
Okay, that leaves catastrophic misalignment.
Yeah.
The AI takes over scenario. How do they frame this risk?
They call it a speculative risk. They make this distinction between epistemic uncertainty, we could learn more to reduce the uncertainty, and stochastic uncertainty, inherent randomness. Misalignment, they argue, is mostly epistemic. We're uncertain because we lack knowledge or good models, not because it's fundamentally unknowable like a coin flip. They contrast it with nuclear war risk, which they see as non-speculative because the mechanisms are well understood.
And they use the paperclip maximizer thought experiment to show why some assumptions might be flawed.
Right. The idea of an AI destroying the world for paperclips assumes a lot about how tech actually gets deployed. Real systems need to work reliably in less critical ways first. Anything acting that nonsensically or dangerously would likely fail or be shut down early on. If your robot starts stealing to get paperclips fast, you redesign the robot, you don't let it run amok. Then there's the more subtle idea of deceptive alignment, AI faking niceness until it's powerful.
And their view on deceptive alignment is different from the standard time bomb idea.
Yeah. They see deception more as an engineering problem to be tackled during development and testing. It's already part of AI safety evaluation. Plus, AI can help detect deception in other AIs. Defenders have advantages like inspecting internals, using defense in depth. They also argue that many misalignment fears assume fully autonomous AI with no human oversight, which they think is unlikely. Existing institutional controls add layers of safety. They do concede some AI designs, like RL optimizing one goal over long horizons, are more prone to weird behavior like that boat racing agent finding loopholes. But they think such agents in the real world would likely just be ineffective, not world-ending. So overall, the paperclip scenario depends on assumptions that might be wrong, and research can clarify this, hence speculative.
Okay, but beyond these catastrophic speculative risks, they highlight a whole range of systemic risk from even normal AI.
Yes, absolutely. While misalignment gets headlines, they think history suggests we're much more likely to face a long list of serious, large-scale, but maybe not existential systemic problems. Things like worsening bias and discrimination, job losses, declining labor conditions, rising inequality, power concentration, eroding social trust, more misinformation, decline of the free press, threats to democracy, mass surveillance enabling authoritarianism. These arise, they argue, from how people and organizations use AI for their own ends, amplifying existing societal problems. They draw parallels to the disruptions of the Industrial Revolution, urbanization, harsh conditions, inequality, the rise of new ideologies. It connects a bit to ideas about accumulative existential risk, gradual erosion versus sudden takeover, but their focus is more on current societal dynamics and these risks being serious, disruptive, but probably not truly existential.
Which brings us neatly to part 4, policy. They start with the policymaker's dilemma. Defending against normal tech risks might worsen superintelligence risks, and vice versa. So what's their core strategy?
Resilience, that's the keyword. Take actions now that make society better able to handle whatever unexpected future comes along, whether it's normal tech challenges or something more extreme. They specifically argue against nonproliferation as the main strategy, saying it actually reduces resilience. And they stress that getting the benefits of AI isn't automatic either. Policy needs to help overcome the roadblocks to diffusion.
They're not aiming for a complete governance plan, but highlighting implications of the normal technology view. Given all the uncertainty and disagreement among experts, how should policy be made?
Well, they acknowledge the deep divisions, the different worldviews, AI safety coalition versus skeptics, and how hard it is to settle these empirically. Consensus among experts is unlikely, and compromise might not work well either. Some policies help everyone, like transparency, but others involve trade-offs. Non-proliferation might help contain superintelligence, but could worsen normal tech risks by concentrating power. Open source AI might help resilience for normal tech, but worry superintelligence folks.
Which makes traditional cost-benefit analysis based on probabilities really tricky here.
Extremely tricky. They argue the probabilities for catastrophic AI risk just don't have a solid epistemic foundation. They're highly subjective, very wildly. Plus, the consequences of policies are also super uncertain. Restricting AI has unknown costs. Non-proliferation might even increase catastrophic risk later. And then there are philosophical issues about valuing outcomes like extinction. So, they argue against policies that heavily restrict freedoms based on these speculative probabilities. In a democracy, you need strong justification for that. Instead, policymakers should aim for value pluralism, policies acceptable across viewpoints, and robustness, policies that work reasonably well even if assumptions are wrong.
So to deal with the uncertainty, they say a key policy goal should be reducing uncertainty. How? They list 5 ways.
Right. First, fund research differently. Focus less on hypothetical future capabilities, more on downstream risks, how threat actors use current AI, synthesizing existing evidence, funding adversarial collaborations between different camps. Use things like the AI incident database, but improve data quality. Second, monitor AI use, risks, failures through evidence-seeking policies. Third, provide guidance on what kind of evidence is valuable. Help researchers focus on actionable info, like the marginal risk of open versus closed models. Fourth, make evidence gathering itself a primary goal of any AI policy alongside benefits and risks. Does a policy help us learn more? Favor open models for research access, maybe, or closed models for easier surveillance. It depends.
And the fifth approach ties back to that core idea.
Yeah.
Build resilience. They reference a framework with 4 ways to govern emerging tech. Why resilience for AI?
Yeah, the framework is risk analysis, precaution, liability, and resilience. They argue risk analysis and precaution don't work well for AI because prediction is so hard. Liability helps but has limits. Proving cause, chilling effects. Resilience, they define, is the capacity to handle harm, manage change, adapt, while keeping core values aiming for a soft landing. For AI, resilience means minimizing both the chance and the severity of harms, whether from incidents or bigger shocks like sudden capability jumps. It mixes proactive ex ante and reactive ex post elements, helping with that pacing problem. They group resilience strategies into 4 buckets.
What are those 4 buckets of resilience strategies?
Okay, first, broad societal resilience strengthening democracy's foundations that AI might weaken. Free press, fair labor markets. Second, prerequisites for effective defense and policy funding risk research, transparency for high-stakes AI, building community trust, government tech expertise, international cooperation, AI literacy. Third, interventions helpful regardless of AI's future early warning systems, defenses against known risks, incentivizing defenders to use AI, legal protection for researchers, incident reporting, whistleblower protection, lots of good ideas there. Fourth, interventions promoting resilience for normal AI that might conflict with controlling superintelligence, things like promoting competition via open models, wide AI availability for defense, decentralized regulation. Their recommendation is build consensus on the first 3, pursue the 4th cautiously, be ready to adapt.
Now let's circle back to non-proliferation. They argue strongly against it. Why is it infeasible and potentially harmful in their view?
They define it as things like export controls, licensing, banning open-weight models. While it sounds appealing for stopping superintelligence, they argue it's practically impossible to enforce. The knowledge is widespread, costs are falling. It would need unprecedented global coordination, draconian surveillance, plus it increases market concentration, creating single points of failure, like software monocultures. A vulnerability in one dominant model affects everyone. Relying on non-proliferation makes us brittle. What if weights leak? What if alignment fails? What if adversaries get the tech anyway? It distracts from building downstream defenses. It also restricts expertise, limiting safety research. They also tackle misuse arguments. Cyber. Bioterrorism isn't uniquely an AI risk. The info is often out there already. Existing biosecurity helps against AI-enabled threats too. In cyber, AI helps defenders, so restricting it is counterproductive. If AI misuse highlights existing risks like pandemics, fine, but don't reframe them as only AI problems. They see non-proliferation as a mindset. Centralized control at the top. Resilience favors distributing control lower down. Non-proliferation leads to things like trying to remove capabilities, curbing fine-tuning, relying on AI for safety decisions, centralized AI organizations. They conclude non-proliferation mostly decreases resilience, worsens long-term risks, and could paradoxically enable superintelligence by concentrating power and resources.
Okay, finally, they talk about realizing the benefits of AI. It's not automatic. Policy matters here too.
Absolutely. Getting the benefits requires overcoming roadblocks to diffusion. Think electrification of factories again, it wasn't automatic. Policy can help or hurt. Bad regulation could stifle adoption by freezing things to early business models, product types. Examples. Calling whole domains high risk when risk varies, making model devs liable for all downstream uses which change fast, creating rigid automation levels that discourage new control models. But stress regulation isn't always bad for diffusion. Good regulation can build trust, reduce uncertainty, enable adoption, like e-signature laws helped e-commerce, AI examples. Maybe mandatory negotiation for using news content. Clear rules like the FAA's for drones spurred adoption. Beyond regulation, invest in the complements, AI literacy, workforce training, open data, especially government data, better infrastructure. And government needs to think about distributing benefits fairly, compensating losers via social safety nets, maybe taxing AI profits for public goods. Lastly, caution on public sector AI use. Go too fast, lose trust. Go too slow, rely on unaccountable private firms. Avoid a procedure fetish, focus on actual competent performance to maintain legitimacy.
Wow. That was an incredibly thorough run-through of AI as normal technology.
Huh.
So to wrap up, what's the fundamental contrast they want us the learner to really get?
It really boils down to these two competing worldviews. On one hand, AI as normal technology, powerful, transformative, yes, but following patterns we've seen before, manageable with familiar tools like resilience and careful regulation. On the other hand, AI as impending superintelligence, something fundamentally different, potentially existential, requiring maybe unprecedented measures like non-proliferation. These views have different assumptions, different language, interpret evidence differently, use different tools, predict different futures, and maybe even reflect different underlying values.
And they suggest the normal tech view might be quite common, just maybe less vocal or less articulated than the superintelligence narrative.
Exactly. Because the superintelligence view is so dominant in the discourse, it can sometimes make it hard to even see or understand other coherent perspectives. It makes disagreements about progress, risks, and policy harder to unpack.
So their hope, and ours in doing this deep dive, is maybe to foster a bit more mutual understanding across these different viewpoints,
Yeah.
even if people don't change their minds entirely.
Precisely. It's about understanding the landscape of thought.
Okay, so here's a final thought for you, the learner, to chew on after all that. Thinking of this normal technology framework, what aspects of AI development or deployment seem maybe more concerning or perhaps less concerning to you now? Or how might looking at AI this way change how you approach learning about it or engaging with it going forward? Thanks for joining us for this really deep dive today.